technical problems are starting. Let's go back to you. There we go. Okay, so I will really mainly talk about this this Python package called scQubits, which is sort of the little fun that I get these days. I encourage you to ask questions. In fact, I did bring a couple of scQubits stickers. So if you ask a question, you can have a sticker. That doesn't count. That doesn't count. Okay. So this package, some of you are familiar with it. Some of you maybe hear about it for the first time. And so I'll tell you a little bit. There will be some redundancy for some, and that's okay. So it's a Python package that is open source, of course. We released it towards the very end of 2019, and I have published 2 papers about parts of the package by now. The download count is growing. I never quite know what to make of it. It is not the number of users. We all understand that. It's hard to get to a user number. We've tried a little bit and failed, but we keep reporting that we accumulate downloads, which is good. And we are growing in terms of not just lines of code, but there's also more and more people who are actually engaged. I think either the next slide or a couple of slides down the line, I have something to say about Unitary Fund and the hackathon that they led just concluded, where if you participated, thank you very much. Oh, it's right here. So in fact, to do a little bit of advertisement for them, you can actually earn money by participating in this quantum hackathon. Again, this year you'd be too late if you're just now interested. But and scQubits is only one of many packages that gets to participate in this, and so that there are bounties that get announced, things where coding is involved, and so if that's something that you enjoy and you want to earn some money even. Please engage in that way. Okay. Now, I'll start actually with saying a couple of things that point towards what we're working on right now, things that are in the pipeline for the next release, and that always includes kind of runtime considerations, like when you simulate these superconducting qubits, especially the kind that Xanthi just taught us about. Then runtime is a consideration, and for us it's matrix diagonalization that is really the bottleneck in almost all cases. And so we're working on improving some of that. Under the hood, so far we just like SciPy, but we've come to appreciate that not everything in SciPy is maybe the state of the art. We've been first of all, learning a little bit, and this may be of interest to you, even if you don't use scQubits, but somewhere you might use SciPy. It has a wonderful list of options, and you're not expected to know them, but you should appreciate that some of these options actually have a major impact on how long it takes for the matrix to be diagonalized, and that sometimes goes in not so intuitive ways, like. You can ask SciPy's eigensh to find eigenvalues for you that are smallest in magnitude or smallest algebraically. Depending on how you shift your matrix, those two could coincide, and probably you would want them to coincide if you want to check and find out that those two options can lead to different runtimes. And that goes even further when you start playing with the sigma, which once you actually specify it, it starts doing shift and vert. So there are options that we started playing with, and it's actually not so systematic and clear which one is best. I would be very happy to report to you that you should always use XYZ, and we would be done with that. But there appears to be a lot of dependence on sparsity of the matrix, on the structure of the matrix, which of course is different from qubit to qubit. So there are places where we've kind of found out that we're losing a factor of 5 in runtime because we're not using the best option for SciPy's eigenstage. Okay. Beyond that, there's actual alternatives, so different eigensolvers. Here's one that we've come to play with and like. I to this day don't know how the authors would like this acronym to be pronounced. Maybe it's PRIMI, or I don't know, but we're playing with it, and it's quite promising in that even there you can sometimes get another factor 5 in runtime, and so that's quite nice. Here's sort of one example where an undergrad actually did some benchmarking in the case of the cosine 2 pi qubit, and sort of you see that what's plotted here is runtime new package runtime, and so smaller numbers mean that PRIMI is winning this factor. So as part of what's in the pipeline is sort of improving upon our package in how you actually might get to specify some of how the diagonalization works. And so Peter Gorzkowski is the one who's leading that effort. He's at Oak Ridge National Lab at this point. And so there will be a new method that you can choose to use and actually determine whether you want to use SciPy or some other package. Peter is in particular, he's particularly interested in making GPU computations available through, I guess QPy is how you pronounce that acronym. I'm so bad with acronyms. And then there's other things that have to do with all that is going to be quite exciting if you do extensive calculations, especially sort of in the realm of optimizing qubit parameters. So lots of diagonalization. Okay, so those are the things that are new, and now maybe more addressing those of you who haven't heard much of scQubits before. I'll try and motivate a little bit what the package actually does, and then if technical problems don't interfere, I will sort of give a tutorial and show you some things live in a Jupyter notebook. And if this fails, well, then it fails. Then it will fail horribly. So some of the tasks that, especially if you're new in the field, you might not have come to appreciate that there's some things that we do all the time and we repeat them. And so at some point in my group's history, we decided that we should make these things that we repeat actually work well and share code. And this is sort of how scQubits started. So clearly, if you're a superconducting qubit person, at some point you might need to know what the energy spectrum of your device of interest is to get intuition about behavior of certain kinds of you might want to visualize wave functions. If you want to know how strongly your qubit couples to, say, an oscillator, you want to compute matrix elements. There's some nice functionality in scQubits to estimate coherence times. And I tend to be careful in not to saying predict, because I think there's always some fudge factor somewhere where we'll try to adjust to whatever comes out in the experiment. We want to certainly be able to model coupled systems of qubits and oscillators, perhaps, and then perform parameter sweeps, maybe one-dimensional, but maybe multi-dimensional parameter sweeps. Let me get my zoom bar here out of the way. We've been improving actually with the last release some of the interface with QTIP. I'll talk a little bit about that, and then I'll just skip over the rest here so that this doesn't take so long. This is the overview, more or less up to date for those of you who are already a little bit more familiar. And I should sort of mention from the outset that parts of the package, there are other packages around, not only going to come from the Stanford group. There's a couple of parts which I will devote some time to in the remaining minutes. Okay. But so the first thing that I'll just show briefly, this is to those of you who are relatively new. There's if you are really just getting started in the field, or perhaps if you're a seasoned PI who doesn't have the time to do a lot of Python programming, but wants to quickly check what the spectrum of a certain qubit looks like, then this graphical user interface is for you. All that you need to be able to do is write 2 lines of code, which I think is doable. You have to import this package and call the graphical user interface, which only covers a small little fraction. Rob is like, oh, I don't know whether this is good enough. Maybe 2 lines is too much. But so this interface covers a tiny fraction of this package. What it does is it tells you about individual qubits, the ones that are hard-coded, and you can tell that there's by now a number of them. This version of the graphical user interface is hiding in a development branch of mine. This is sort of the thing that I get to do when I can't fall asleep again after 4 o'clock in the morning. The same functionality exists in what's currently released. Maybe like Fluxonium, clearly the arrow Fluxonium these days, and so you get to look at energy as a function of some parameter. It doesn't have to be flux, maybe EK. If you want to see how your spectrum changes, that works as well. You can look at wave functions. No problem. We put a little bit of effort. We started effort, and we hope that we'll get help. Like it would be nice to actually have some example parameters that I'm going to start playing with, and I want to get back to maybe what the first Fluxonium experiment was like. Maybe those were default anyways. For each qubit, information on what are typical parameters, if that's what you want to call it. You can look at matrix elements. Again, for coupling, that's a good idea. And for those of you who are color challenged like myself, you even get to display like the values on top. I always find super helpful. Fluxonium matrix elements, usually the plot that sort of shows J. And so this graphical user interface just allows you to explore and discover, for instance, in Fluxonium, that you can get to funny parameter regimes that haven't been explored in the experiment yet. And I'm going to talk much about that, but it's kind of fun to explore the world of areas that we think we know and discover little things that we didn't realize before. Okay, and then last but not least, the thing that is problematic as I'm running Zoom on this machine, which slows my machine down significantly. So we'll sit here until there is a couple of seconds.
Yeah, so you're waiting.
Yeah.
For the parameters. For the parameters, is that like a CSV file, and like if I was to make a commit, how do I update it?
Yeah, that's a really good question. I think we'll want to improve on that. Right now, it is sort of not as well. Yeah, no, it's not a separate file. So if anybody is interested, I would be very eager and excited to help personally. And as soon as there's contributions, you can, in the beginning, I think the best way would just send me an email, say this is my favorite paper, or I wrote this, or I made this device. These are the parameters, and then in the beginning I'll put them in, and as soon as there's enough contributions like this, we'll find a streamlined process. Yep. Thank you. All right, and then so the graph actually came out so you to see for this Fluxonium particular contributions to T1 R. Good. Let me jump back to my slide here. That's not where my slide. Oh, this is interesting. I get to jump back into what's in presentation mode. Usually that works just fine. There we go. All right. We talked about the GUI. Don't need to do that here. So the next thing I'd like to chat about a little bit is Hilbert space and parameter space classes. So you are advanced researchers, all of you, and if you're interested in anything to do with qubits, it's going to involve more than one qubit, most likely. And so there's a lot of functionality in the package, which we try to document actually quite extensively, but I know that we don't all like to read documentation. So I'll give you a little spiel on some of the things that are possible. Some are oftentimes overlooked. And so I'll do a little bit of that again in a notebook over here, I hope. So number one, barbecue. Yeah. Okay. So I think I had already initialized some of this, which is good. So suppose that suppose you wanted something simple in the beginning. Let's couple a transpond to an oscillator, right? And now this is more than 2 lines of code, but actually not that many. And so let me just show you how this works. We would make a transpond and an oscillator. You can do that purely programmatically, but if you sort of like a reminder of what these things are and what the parameters are, then you can bring up this little user interface where it shows you the parameters, it creates the particular qubit, and you get to edit the values in here, and it updates them automatically. So we now have a transpond with those particular parameter values. We have now an oscillator, and this is massively big because it's not scaling right. And then, so for the Hilbert space, again, you can do this in multiple ways. In the user interface, the way this goes is you can select the subsystem you want to be part of the Hilbert space, both of them, obviously. And then you get to say, well, what kind of interaction we have between them. And that should be quick, right? A transpond passively coupled goes to the it'll couple to the oscillator, couple to A with the dagger. I'll put A and A at the Hermitian conjugate. And if the coupling strength is a little bit larger than 0, then life is the better. And then we create this Hilbert space. And so now this object that says these 2 systems are inside that Hilbert space. There's interaction between them. And you can ask for the Hamiltonian, for instance, that goes quickly. And you see that immediately actually pops out in the format of a QTIP object, right? So this is not just a NumPy array, this is on QTIP side, where it records that this, thankfully, my is Hermitian. All the entries are there. You can ask for eigenvalues and you'll get them. And then there's some functionality which could be helpful in your research. So already on the Hilbert space size, you get to generate a lookup, which does something very simple. Our assumption is that very, very frequently, you're going to work in the dispersive regime, where it actually makes sense to have labeling of states by sort of bare product state labels, right? So what the computer does, it'll just say eigenenergy 0, 1, 2, 3. It'll label them in this manner, but it would be nice to actually switch back and forth between kind of saying this state is the one where transpond is in the second excited state and there's no photon in the cavity. And this is what this lookup does. So, a little loop here that says, so for the lowest addressed in 0, 2, 3, 4, 5, tell me, please, what are the bare indices? And so it tells me, fortunately, I did expect that. And then my second system is the oscillator, the first system here with the transpond. And so you can tell how the excitations stack up as you go through this. Likewise, you can sort of ask for energies by, but there are lots of little functions that allow you to do this translation back and forth. That's something that people sometimes overlook, and they think they have to run this, and it's actually all there. Good. Now, the next step, oftentimes, at least for us, is you now have this coupled system. Maybe I need to understand how this behaves as a function of external parameters. And so let me briefly come back here. I thought I had a slide for that. This worked. Good. Oops. There we go. So suppose that you want to run a multidimensional parameter sweep. In easy cases, if it's just one-dimensional, this could be as simple as changing a parameter that is actually a parameter of one of your qubits, like EJ or NG. It doesn't have to be. I think in one of the examples that I'll show, I imagine you have two flux-tunable transmons, but maybe you don't have local flux-biased lines, so there's a global field, and yet the two squid loop areas are different. And so you can cook up situations where the parameters are not directly attributes of your class instances, and that's fine. So the ingredients that would go into specifying multidimensional parameters are you name your parameters, you give them names, and you specify the values over which you want to sweep. And then there's an update function in which you specify what these parameters actually do, right? If it's something of the sort that I just described with my global field that penetrates two squid loops of different areas, you'll have to actually enter information on how the updating should work. And then optionally for each parameter, you can specify which subsystems are involved in the update. Like suppose that I do have two transmons, but it's the EJ of transmon 1 that I want to modify. I don't want to rediagonalize transmon 2 every time that the EJ of the first transmon changes. And so that's information that you can provide, and that'll speed everything up. And so once you do that, I'll show you one example in a second. You get an object that is a parameter sweep object, and it actually pre-computes a whole bunch of data for you that you can access as if sweep was a dictionary. So it'll go for you all the bare eigenenergies, the dressed eigenenergies, likewise eigenstates, and it detects whether if you have a system that is a qubit and an oscillator, it'll pre-compute that shift over ranges where everything is dispersive, and so you can extract those very easily. And you can run custom sweeps on top of that. So once you've initialized this and this data is pre-computed, you can add your own sweep that can access this data as well. So for instance, if you wanted to sweep over T1 time, right? This is not pre-computed directly, but you can make it so, and you can use the eigen. Well, T1 was not a great example, but you come up with something that you want to sweep over that might want to use some of the bare data that is already present in the first run. Okay, and let's see. I do have one to show that. Right. So I don't want you to worry about reading this code. I'm just going to describe to you the system that I made, and then I'll show you, hopefully, I'll show you a little bit of plots that I think are helpful and also helpful for fitting experimental data. So the system that I've initialized here, so don't stare at the code, is two flux-tunable transmons. They're both coupled to the same oscillator mode. They do have different squid loop areas. And so the nice thing that the package makes available for you is you can sort of try and mimic a little bit of what you might see in photon spectroscopy, right? So if you don't do anything special, usually these plots look a little land. And what SEQ do is to say, well, in the spaghetti land, please highlight for me only transitions that belong, for instance, to transmon 1. So here in the transitions that are state or the second say, well, I want the oscillator as well. Did I call it oscillator or resonator? That's what second. I call it resonator. Okay, let's do that then. So it now the things which correspond to 1 photon, 2 or 3 photons. You can enable or disable sidebands. You can actually specify that maybe if you are worried that part of the time you're thermally excited, you can plot the transitions that you see if you were to start in the, let's say, the first excited transpond state. It's more interesting for fluxonium around half integer flux where thermal excitations can matter. And so there's a lot of functionality there that should allow you to very quickly explore spectra that you might be generating without kind of wondering which of the many curves belong to what. So again, in the background, what happens is there's this lookup going on where you identify eigenstates that the computer, eigenstates and eigenenergies, the computer just labels by 0, 1, 2, 3. But once you have the mapping to bare product state labels, you can actually get some insight and information. And I don't have to say anything about this. Yeah, I can say that. I mentioned that there are two transponds. We can briefly look at transpond 2. It has a difference with loop area, so it has a different period. And there we go. So that one's at lower end. See the postal conditions there. Okay, how am I doing on time? This? Oh yeah, and just sort of mentioning this with a little bit of pride maybe, but also sometimes being scared as to what will happen in the future, because as an open source package, like everybody can just do with our code what they want. We are currently a dependency for IBM Qiskit Metal, so they make use of this Hilbert space and parameter sweep functionality, and we do talk with them and try to be friendly, and we'll see how that goes overall. And then last but not least, I wanted to talk a bit more about this idea of having scQubits help you quantize circuits, right? So you draw a circuit and you ask yourself what is the Hamiltonian for that? And just as a reminder, oh, I thought I had fixed this animation. So just as a reminder, this is a systematic procedure, but it's not always easy and sometimes rather tedious. So you start from a circuit where you want to end up is probably with energy spectra, matrix elements, and all that kind of stuff. And so you go through, maybe you follow Michel's lecture notes or one of the newer papers, and you make your way from a circuit representation, the assumption being that lumped element description is valid, to a Lagrangian and Hamiltonian on the classical side, and you quantize. And as nice and simple as this little roadmap looks, in reality, there's actually quite a few steps. So I'll remind you maybe a little bit. Did I shift this bar out of the way? So just to give you a flavor, if you haven't done circuit quantization by hand in a while, if your circuit has more than 2 nodes, it's actually fun. So you have to think a little bit about how to, well, the enumerating nodes and branches is nothing to think about, but they're the things about if you have multiple loops, you have to make sure that you incorporate all the constraints for those. Michel suggested long ago to do that with spanning trees, and that's a fine idea. But even when you do that, there's still things left that are some maybe not even discussed in great detail in Michel's lecture notes. Like, suppose you have a circuit like 0 pi. You heard a couple of moments ago that there are multiple modes, multiple degrees of freedom. And they are different in nature. You saw that there was a transpond-like degree of freedom, there was a fluxonium-like degree of freedom, there was a harmonic oscillator degree of freedom. But those didn't, like when you write down the Lagrangian in node variables or branch variables, those modes will not just stare at you and say hi. You'll actually have to identify them. And you have to sort of think of this in this case, maybe a 3-dimensional space, right? It's spanned by 3 variables, and only in one particular direction, when you orient your axes correctly, will you discover that one direction is perfectly periodic. And you'll want to identify that direction because if you don't, then it becomes rather awkward to specify boundary conditions for your wave function, right? And so that's something that can be done systematically. That's something that scQubits does systematically, and that way you can indeed study the behavior of energies as a function of offset charges and such. It also tries to identify free or cyclic degrees of freedom and eliminate those. And then sometimes, depending on the circuit, there's actually freedom left. And that, in my mind, is a sort of open research topic where whatever freedom in kind of orienting your axes in this multidimensional space is left can influence how efficient your diagonalization will be. Also, how intuitive the Hamiltonian looks like in the end. And so there's nothing particularly smart in scQubits yet. You do get the option to specify your own variable transformation that overrides the kind of the default choice that scQubits will make for you. But I think there's more that we want to learn and improve in that direction. And then from there, once that is done, you understand how the Legendre transforms work. It involves inverting the capacitance matrix. You'll do canonical quantization. And once you choose a basis in your Hilbert space in some appropriate way, you will represent this Hamiltonian operator as a matrix that you can stick into, I don't know, SciPy or Primi or whatever. There we go. I will skip over this. So how do you specify a circuit? scQubits has one way to do this. It has a specific syntax. There's actually, instead of talking a lot about the syntax, I'll just briefly say you specify what kind of element you're talking about. The next two columns are the two nodes. So apparently there's a Josephson junction that connects nodes number 1, 2, must be this one, and there are parameters that specify the energy in gigahertz, which is the default. You're happy to, there's functionality to change from gigahertz to something else if you're courageous enough to do that. But there is actually work that has nothing to do with my group, but in undergrad, I think at Yale, I'm staring at Rob because I sort of assume that Rob knows all undergrads, which is maybe not true, but probably Ben has come across your way. And so he wrote this fun package that uses, I think it's PySide 2 based. It's a little confusing based elements on this, and then it exports this in a format that scQubits knows how to interpret. So if you like that better, then you don't even have to learn the syntax that I showed you a slide ago. Okay. And then let's see. So on this one, I have a bunch of slides, I think, instead of jumping into a live notebook, just to give you a flavor of how quick and easy this is. So once you've defined your circuit, the example that I've picked happens to be 0 pi. It's a toy example in the sense that that's actually hard-coded in scQubits as well, but at least we know what the outcome should be. And so you initialize this object, and then you can ask for things like, what's the symbolic Lagrangian? Not all of the output is sort of in the nice form that a human being would maybe prefer. For the Lagrangian, I think I don't care that much because we don't do a lot with it. You'll see that down the road, the Hamiltonian actually looks quite nice. This is still in node variables, which are sort of not the right variables for 0 pi anyways. So you can ask for the new variables that scQubits picked, which since it knows nothing about literature, right? It didn't ask Xanthi about the names. It doesn't know about zeta and chi and no, sorry, it's zeta, phi, and theta. It just says theta 1, theta 2, theta 3. But we could identify here now which one is which. And in fact, it allows you to extract what the variable transformation was and also what kinds of variables are present. So it detects that the one is now the one that is periodic. Here you have confining boundary conditions. And it's already eliminated the I think sigma mode is what Xanthi called it in her talk, this overall cyclic degree of freedom that can be eliminated. And then you get some symbolic Hamiltonian back. You see that scQubits does insert fluxes when it discovers loops, inductive loops. So there's an external flux that can be tuned. It also detects that with the periodic degree of freedom, there comes an offset charge, which is NV1. And so with that, you're kind of ready to ask for eigenvalues and eigenstates. You get to plot them. And then this entire class itself is compatible with being stuck into parameter sweep and being coupled to other systems if that's what you want to do. Or you can stick everything into just one big circuit that you define in this way. Both works. There was I forgot to put this on the slide already yesterday, and then it escaped me again. There's one important remark. There are cutoffs in various places, right? So even if you think about the Hamiltonian of a transmon, that matrix is actually infinite dimensional. And if your computer is not much better than mine, your computer also doesn't like infinite dimensional matrices. So there are cutoffs left and right. On our end, we are very afraid of a situation where we attempt to be too good and sort of get you into a place where you feel like everything that the package spits out is true. So for that reason, we didn't even put in any convergence checks. So you're the person who does convergence checks. We're rethinking some of that strategy, but I think overall, with anything that is more complicated than a transmon and has multiple modes, like there will be multiple cutoffs, and there's probably no foolproof thing that will just do this for you, and you don't have to worry. So you do have to worry about cutoffs. Every qubit, also the circuit class, has these cutoffs, and when you use the package, you should you can start with a default. If you're not in some outrageous parameter regime, maybe the default is actually okay. But you should check by increasing the cutoff or cutoffs and verify that the result that you get is all the eigenenergies, for instance, are converged. Okay, I'm running out of time. This was the I'm completely out of time. I am completely out of time. Okay, then I shut up. I'm not going to talk about hierarchical diagonalization. I'm just going to say thank you to people and organizations from which we've received money. And then last but not least, sort of completely off topic, Northwestern now, as part of the SQMS Center, has a brand new fridge in the basement, which is actually working. I hear that's not a given all the time. Unfortunately, the person who's overseeing this effort, Nick Zelev, is moving, and so we're very much looking for a person who might take over in the fall. So if you know of someone, please tell them. And now I'll really shut up. Thank you.
Great talk. Can we open the floor to questions?
Are you going to hand out?
Anyway, you could include like resistors in the model.
Resistors in our model.
Like open quantum systems, essentially. Like
So to me, that this sort of belongs on the side of intuitive and dynamics, right? Where for like you're talking about loss, which I would stick into jump operators in QTIP. So there is functionality where I can briefly jump here. I would check for that. So if you check out the last release, then you'll find that there are now helper functions which give you operators in the dressed eigenbasis. So for instance, if you had one N operator is not a very common jump operator. But if you had an oscillator as part of a joint Hilbert space and you want the A operator to be the jump operator, then in a composite system, in the past, you would have had to kind of figure out how to wrap this in identities, and it was a little bit of a nuisance. But there's functionality now that streamlines this. So you'll have to determine what your jump operators are. Not all of that will correspond to just simple resistors, but you can certainly then go on the Q-tip side, simulate the effects.
Possible thinking at the circuit level to have an algorithmic way to determine like place like resistors like or output lines and then checking like what are the jump operators.
So that's I would like to learn more. I was taught a long time ago that we avoid resistors as much as we can. If there's interest in including them, there's some things that I would like to understand better and what you have in mind.
So since he asked about resistor, maybe I can ask about like QPS or non-reciprocal device, maybe it's like a dissipationist device.
Andras is there. So Andras is leading a project that I'm fortunate to be part of that is looking at quantum facelift junctions. He actually with a colleague wrote a paper that discusses some of the interesting things that happen in circuit quantization if you work with quantum facelift junctions. We think that we have a sort of equivalent scheme that is easier to integrate into the packet, but there are some caveats. Like there are when you think back about the beginning of circuit quantization and why it is that you actually use flux-based variables as opposed to charge-based variables, it has something to do with the fact that the energy of a Josephson junction, EJ minus EJ cosine phi, well, it's nonlinear. That's not really the big problem. The problem is that it's not invertible over the full interval from 0 to 2 pi, right? So if you wanted to try and use charge variables, it maybe it's not impossible, but it's nasty. And so we don't do that, and we use flux-based variables. For a quantum facelift junction, it's the other way around. You would actually prefer to use charge-based variables as opposed to flux-based variables. And so as soon as you have circuits that combine both quantum facelift junctions and Josephson junctions, there will be some tension. And so Andras' paper points out one way in how to handle this. There are alternatives, but it's not quite as straightforward as one might think in the beginning.
How about the non-reciprocal device, like gyrator stuff?
Yeah, that's also complicated.
Yeah,
but if there's as soon as we have the sense that this is not something that 1 or 2 people worldwide work on, but sort of a critical mass of people, we'd be happy to talk and engage. But I've come to appreciate with packages like this that it's important to first make 90% of the people happy and spend time on that as opposed to making like the 5% happy that or 10 is the math that do quite exotic things.
Thanks.
Thank you. Well, I think we're running out of time, so if you could please thank the speaker again.
Oh, yes.
Okay, just while we set up, our next speaker is Ryotatsu Yanagimoto and Rajveer Nehra from Stanford.